Analytical. Chemistry.
Hey everyone! Welcome back to the channel. If you're new here, I'm Rona. And today we're going to talk about something really exciting and super important in the world of science and research. It's about how to develop a standard method.
Developing a standard method.
Whether you're a scientist, an engineer, or just curious in mind, understanding how experiment are standardized and optimized can be a game changer. We'll cover everything from the basic of what a standard method is to be the detailed process of how you can develop one yourself. So, sit tight because this is going to be a deep dive. Let's start by understanding what we mean by a standard method. A standard method is a set of procedure used to conduct experiment or test in a consistent, reliable, repeatable way. So, think of it as a recipe for an experiment. You follow this recipe and you should always get the same outcome, no matter who's cooking or, in this case, who's running the experiment. Why is this so crucial? Well, consistency is key in science. If one lab gets one result, another lab gets something completely different, we can trust those findings. And when experiments are inconsistent, things get messy. Whether it's in scientific research, industry application, or even in your day-to-day work. Imagine if a factory was manufacturing medicine and the production process wasn't standard or standardized. The result could be unreliable, potentially dangerous, and definitely costly. So, developing a standard method is all about ensuring the process are reliable, precise, and can be repeated by anyone, anywhere. Now that we know what a standard method is, let's get into the nitty-gritty of how we actually develop one. The first step is optimizing the experimental procedure. This is where we refine the method to get the best, most reliable results. One of common techniques used in optimization is called response surfaces. This is a fancy way of saying we create a graph or model that help us understand how different factors like temperature or chemical amounts affect our results. By analyzing this data, we can figure out the optimal condition for our experiment. Thanks for the breakdown. It is clear how important these models are for figuring out the best experimental conditions. Next up, let's talk about searching algorithms. These are computer programs that help us find the optimal settings for our experiments without testing every single possibility manually. Think of them like a smart assistants that can save you hours, if not days, of trial and error. Instead of manually adjusting one factor at a time, searching algorithms systematically explore different conditions and narrow down the best combination quickly. Pretty cool, right? Now, let's discuss a big balance in optimization: effectiveness and efficiency. You want your experiment to give a great results, but you also want it done quickly and without wasting resources. It's like cooking. You want a delicious meal, but you don't want to spend hours in the kitchen or use all your ingredients. Finding the sweet spot where your experiment is both effective and efficient is one of the hardest parts of optimization. You might get fantastic results, but if it takes too long or wastes too much material, it's not really practical. Let's dive deeper into two common optimization methods: one factor at a time and simplex optimization. In one factor at a time, you change one variable like temperature while keeping everything else constant. So this allows you to pinpoint exactly how each factor affects the result, but it can be slow. While simplex optimization is different. It allows you to tweak multiple factors at once. This method is faster and often more effective when you're working with complex systems where several factors interact with each other.
To optimize any experiment, you also need to rely on various models, like mathematical, theoretical, and empirical models. Let's break them down.
Mathematical models predict outcome based on formulas, while theoretical models are built on scientific principles that explain how things should behave. And how about empirical models? Actually, they're data-driven, created from real-world results. And all of these models help us fine-tune the experiment to make it as effective as possible. Once we optimize the method, it's time to verify it. Verification means making sure your method works consistently and reliably. There are a few key ways to do this. First, you need to check single operator characteristics. This means that if the same person runs the experiment multiple times, they should get the same result every time. It's all about reproducibility. Consistency is key here. If one researcher can reproduce the result, the method needs some tweaking. Next up is blind analysis. In this step, you test samples whose result you already know, but you don't know which sample is which. This ensures you're not influenced by your prior knowledge and test the objectivity of your method.
Blind analysis is a great way to check if the method is giving you accurate result free from bias. Now, we move on the final step, which is validating the method as a standard method. This step is all about proving that the method is not only effective but can be used by anyone, anywhere, and still produce reliable results. One way to validate your method is through two-sample collaborative testing. This means different labs or researchers test the same method using the same samples. If everyone gets similar result, that's a good indicator that the method is solid.
Collaborative testing helps ensure that the method works universally, not just in one specific environment.
Collaborative testing is often paired with ANOVA, a statistical method that compares results from different labs to see if they align. If the results are consistent across the board, that's how we know that the method is validated. Finally, we'll look for the reasonable result for the collaborative study. If your method gives consistent result in multiple labs and conditions, you've got yourself a validated standard method. So there you have it, from optimizing the procedure to verifying and validating. Developing a standard method is crucial for consistency, accuracy, repeatability in any experiment. This process ensures that everyone, anywhere, can follow the same steps and get the same reliable results.
If you learned something new today, make sure to hit the like button and subscribe for more science content. And leave your thoughts or questions in the comments below. I'd love to hear what you think about standard method or any question you have on this topic. So, okay, thanks for watching and I'll see you next time.